Hello, this is Mr. Best. Welcome to Chapter 5, Homework Questions 17 through 23. Question 17. For each triangle below, write an equation related to the reference angle with the two side lengths of the right triangle. Then solve your equation for x. So we are working on using our ratios, tangent, sine, and cosine. And so on part A, if we're using the angle of 22 degrees, then we need the opposite side. So that represents the opposite side, and then the 17 is the hypotenuse. So we want to use the sine ratio. So sine of 22 degrees is equal to x over 17. So I will solve these equations for the exact value, and then I'll plug it into the calculator. So this would give me 17 times sine of 22 degrees is equal to x. And so when I plug that in the calculator, I get x as approximately 6.37. And it doesn't have any units, so we'll just say it is units. On part B, if we're using the angle of 49 degrees, once again we have opposite side, but we also have the adjacent side. So on this one, we will use the tangent of 49 degrees. And that's equal to 7 over x. And so, as I said before, I'll solve for the exact value first, and then I'll plug it into the calculator. So I'm going to multiply both sides by x to get rid of the denominator, and then I will divide both sides by tangent of 49 degrees. And so 7 divided by tangent of 49 is 6.09, approximately 6.09. Once again, we'll just call units on this one. And then on part C, we have 60 degrees, and we have the adjacent side. And 6 is the hypotenuse, that's the longest side. And so we can use the cosine ratio. Cosine of 60 degrees is equal to x over 6, so it's the adjacent over the hypotenuse. Solve the exact value of x by multiplying by 6, so 6 times cosine of 60 degrees is what x's value is exactly. But if we plug that into the calculator, we're able to get a value of 3. So, and it's not an approximation on this one, x is equal to 3 exactly, which means cosine of 60 degrees must be 1/2. Question 18. While shopping at his local home improvement store, Chin noticed the directions for an extension ladder state. This ladder is most stable when used at a 75-degree angle with the ground. He wants to buy a ladder to paint a 2-story house that is 26 feet high. How long does his ladder need to be? Draw a diagram and set up an equation for this situation, and make sure you show all your work. All right, so let's get a diagram set up. So we have our lovely house here, and let's make it a little bit bigger here. And we want to paint all the way to the second story here, so we'll create this ladder. Alright, and we know that it's most stable at 75 degrees with the ground. It says that right here in the directions. And then also that the house is 26 feet tall. So what we want to know is we want to know what the length of the ladder must be for him to be able to accomplish this task. And so if we have 75 degrees, the 26 represents the opposite side, and the h would represent the hypotenuse. So that means we could use sine of 75 degrees is equal to 26 over h. And then we just need to solve this equation. We'll multiply by h first. That doesn't solve the equation because it just gets the h out of the denominator. We're not done yet. We need to divide both sides by sine of 75 degrees. So the exact answer is 26 divided by sine of 75 degrees, and then we can plug that in our calculator to get an approximation. And so the approximation is 26.92 if we round it to the nearest hundredths. So 26.92 feet. And so once again, make sure we do answer the question as to how long does the ladder need to be. You know, it needs to be at least 26.92 feet, or we could even round up to 27 feet for a ladder. So the ladder needs to be at least 27 feet long. And so make sure you do answer the question there. I went ahead and kept it with the 26.92 feet. If you show your work in this problem, then it would be okay if you said the ladder needs to be at least 27 feet long but you have to make sure you're showing your work as to why you would have rounded to 27. Question 19, examine each sequence below. State whether it is arithmetic, geometric, or neither. For the sequences that are arithmetic or geometric, you need to find the formula for T of n or A sub n. So on part A, we're going from 100 to 10 to 1. So you might recognize that that hey, I'm dividing by 10 each time. But we're looking for arithmetic, which means repeated addition, or geometric, which is repeated multiplication. So if we're trying to find that ratio, we don't want to say it's 10. We want to divide by 10 or multiply by 1 over 10. So we need to make sure that the common ratio here is 1 over 10. We know that the first term is 100. So we can write it in first term form, or we could go back and find term 0 as well. So we could go back and say, well, this is A sub 1. So if I want to know what A sub 0 is, I just multiply by 10 to get 1,000. So there's a couple different ways that we can write this, and I'll show you. All right, so we said it was geometric because we are multiplying. The first one, this is first term form. And all that means is that we're using the first term, so the A sub 1, that's what the 100 is. That's the first term. We don't have to go back and find term 0. And so that would be 100 times the ratio 1 over 10 raised to the n minus 1. And the reason you'd have to subtract 1 is because you're starting with the first term. Now, on the second one here, this is using term 0. So I started with 1,000, which would be what we usually call our initial, that starting value. Still 1 over 10, but raised to the n. So now when I plug in n equals 0, I get 1 times 1,000, which is 1,000. So either one of them works. It's just one's the first term form, and the other one just starts with term 0. On part B, we have 0, negative 50, negative 100. So you can see that the common difference is negative 50. You're adding negative 50 each time. So what that means is that this one is arithmetic. And once again, you can start with your first term, or you can go back and start at term 0. So this would be term 1. If you want term 0, you'd have to go back, and that would be 50, because you would just add 50. And if we use the first term form, we would have, this time I'll use A sub n just to kind of change the form, because it doesn't matter which one we use here, is equal to, and since I'm using the first term form, I'm starting at 0, so this one will look a little different just because of that. But then I am subtracting 50, and then I'll use that n minus 1 again, as I did on the geometric sequence. This is the first term, and that's because you're starting with the first term as to when you plug in 1 minus 1 is 0, times negative 50, and then 0 minus 0 is 0. If I choose to do the term 0, then A sub n would be equal to 50, and I'd still subtract 50 each time, but then I could just multiply it by n. So once again, if you think about this, if I take this expression right here and I simplify it, what is that simplified to? That's negative 50n plus 50. Are these two the same? And they absolutely are. They're in a different order, but they're still the same thing. So one is simplified a little bit more than the first one. So lots of information there. I apologize, but just getting you to look at arithmetic and geometric again from algebra. Question 20, the spinner at the right has 3 regions A, B, and C. To play the game, you must spin it twice. If the game were played 80 times, how many times would you expect to get A on both spins? Use a tree diagram or an area model to help you answer the question. So 2 spins, I'm going to use an area model. There's 3 regions. So 1, 2, 3, 1, 2, 3. A, B, and C on both sides because it is the same spinner. and A is 1/4. B, now it says 135 degrees, so what's 135 degrees out of a total of 360? What does that simplify to? And that will give you the ratio, or the fraction ratio, whatever that you would need. And so that would simplify to 3/8. So B is 3/8. And then C, we could figure out, it looks like it's 3/8 again, but to make sure, this is 90 degrees. So if you take 360 and you subtract 90 and you subtract the 135, you get 135. So C is also 135, but we did want to verify that. We didn't want to assume it. So we got 1/4, 3/8, and 3/8. Same thing on the other side, 1/4, 3/8, and 3/8. Now, to win, how many times, well, it actually says how many times would you expect to get an A on both spins. So I'm only interested in this first box here where I get an AA, and that's 1/16. So that's how many times I'd be expected my probability in terms of winning. Now, the question goes beyond that. It says if the game were played 80 times, how many times would you expect to get A on both spins? So I'm not going to fill in the rest of the boxes because I don't need them for this, but how do I find out of 80 spins if I'm going to win 1/16 of the time? How do I answer that question? And so since my probability is 1 out of 16, then I can just multiply by however many times I want to spin, which in this case is 80, and then when you multiply, you get 5. So I'd be expected to win 5 times out of 80 if or I keep saying win, but I'd be expected to get A on both spins 5 times out of 80, with my probability being 1/16. So make sure you do answer the question there and you show your work. Question 21. Lori has written the conjectures below. For each one, decide if it is true or not. If you believe it is not true, find a counterexample for that one. And we did one of these the other day in the homework. So an example that proves that the statement is false. So for part A, if a triangle has a 60-degree angle, it must be an equilateral triangle. And if we only know one of the angles is 60, that means the other two can add up to 120. So no, that's false. We could have a 30-degree angle, a 60-degree, and a 90-degree. That adds up to 180, and it's not equilateral. All the angles are not the same, and the side lengths are not the same. Part B. To find the area of a shape, you always multiply the length of the base by the height. So to find the area of a shape, it doesn't say specifically what kind, so no, that is false. We know, that's true for rectangles, that's true for parallelograms, but, a lot of other things that's not true for. And for a counterexample, I'll do a trapezoid. The area of a trapezoid is 1/2 times the height, and then the sum of the bases. So that's not always true. And part C, all shapes have 360 rotation symmetry. And this is true because 360 degrees is a full rotation. So no matter what, if you rotate an object 360 degrees around, it's just going to go right back to its original location. Question 22, multiply each polynomial. That is, change each product to a sum. So we'll do these a couple different ways just to show you. The first one I'm just going to distribute, which means I'm going to take my 2x and I'm going to distribute to the 3x minus 2. So that would give us 6x squared minus 4x. And then I have to take the 1 and also distribute that as well. So that would be plus 3x minus 2. And so when I combine my like terms, I have 6x squared minus x minus 2. Now, another way we could do this on part B, I'm going to scoot this down here, is that we could create a generic rectangle. And sometimes organization-wise, this looks a little bit easier and can be a little bit easier to be able to see everything. So 2x plus 1 on the left side, or in this case on the left side of mine, 3x squared minus 2x minus 5. And all we did is take the length of a rectangle and break it up into its 3 parts, and the width, break it up into its 2 parts. And now we're just going to find the individual areas of each of these rectangles. So this is 6x cubed. Then you have minus 4x squared, and then minus 10x. And then when you multiply them by 1, 3x squared minus 2x minus 5. And then we just combine our like terms. And so when we look for this, you might see some things. We have these two are like terms, and then these two are also like terms. All right. And so when we simplify and we combine the like terms, we get 6x cubed. We always want to start with the highest exponent, minus x squared, minus 12x, and then minus 5. So this represents the area as a sum. It's given to us as a product, and it's equal to the sum. So let me do this real quick. So this is equal to 2x plus 1 times 3x squared minus 2x minus 5. So this is the sum of its parts, and this is the product. All right, on part C, I'm going to just use the distributive property again. This would be me negative 3xy plus 3y squared. Negative 8 times negative x would be positive 8x, and negative 8 times y would be negative 8y. And then when you look at this one, there are no like terms, so this would be my final answer. There's nothing else that we can combine. And then on part D, I'll use the generic rectangle on this one, give you two of each. This one has x minus 3y on one side and x plus 3y on the other side. And watch what happens on this one. We get our x squared, we get negative 3xy, positive 3xy, and then negative 9y squared. What happens to your like terms on this one? You'll notice that they cancel out. And so, get rid of that line there. That means the final answer would be x squared minus 9y squared. And I'll write kind of the full answer here. That's equal to x minus 3y times x plus 3y. And that's really the way I should have wrote the other ones on top as well, where 6x squared minus x is equal to 2x plus 1 and 3x minus 2. So that's how you multiply polynomials, using the generic rectangle or the distributive property. Question 23, examine the triangles below. Are the triangles similar? If so, show how you know with the flowchart. If not, explain how you know they cannot be similar. So there's only really two triangles up here since they didn't tell us which ones we're looking at, and it appears we're looking at triangle ABC and DEF, and we're trying to see if they are similar. Now we do have two parallel lines, so some things that we can start marking, even though we don't know the specific angle measures. We know that this angle and this angle are congruent because they are vertical angles. We also know that this angle and this angle up here are congruent because of corresponding angles, where you have a line cut by two parallel lines, which means this angle is congruent because of corresponding angles or vertical angle. So what does that tell us about the triangles? That allows us, I'm going to get rid of this one and this one because those are the ones that are not part of the triangle. And so now we know that the measure of angle C is equal to the measure of angle D, which is important to prove that they're similar. Now it doesn't look like either of the other angles we can look at, so now we have side lengths. So for the side lengths, we have to know that they are in proportion. So for example, let's take this side length BC, and this side length that matches up with that would be DF. And so 4 over 5, that would have to be equal to this side length of 6 over its corresponding side length of 7.5. So are those equal to each other? Well, 4 over 5 would be 0.8. And so what's 6 divided by 7.5? And that's also 0.8. So they do check out. Their corresponding sides are in proportion. And this does represent side angle side similarity. So it does work. So let's go ahead and create our flowchart. We have I kind of already have it written down. I'm going to rewrite it in a flowchart form though. The measure of angle C is equal to the measure of angle D. We also know that the ratio of BC over DF is equal to 0.8, and AC over the ratio of DE is also equal to 0.8. So we have measure of angles, side lengths that are in proportion, and this all goes to prove that the triangle ABC is similar to triangle, make sure you match them up right, EDF. And let's fix this one. That's actually EFD. Because A goes with E, C goes with D, and B goes with F. There we go. And we know that by side angle side similarity. And don't forget to draw on the arrows that the three bubbles above go to prove that the triangles are similar. And also don't forget about the side angle side similarity that you need to write on the bottom of that last bubble.